In this video, the following topics will be covered: classification by backpropagation and support vector machine and k nearest neighbor. Backpropagation is a neural network learning algorithm. Backpropagation algorithm performs learning on a multi-layer feed-forward neural network. It iteratively learns a set of weights for prediction of the class label of tuples. A multi-layer feed-forward neural network consists of an input layer, one or more hidden layers, and an output layer. Each layer is made up of units. The inputs to the network correspond to the attributes measured for each training tuple. The inputs are fed simultaneously into the units making up the input layer. These inputs pass through the input layer and are then weighted and fed simultaneously to a second layer of neuron-like units known as hidden layer. The outputs of the hidden layer units can be input to another hidden layer and so on. The number of hidden layers is arbitrary, and the weighted outputs of the last hidden layer are input to units making the output layer, which emits the network's prediction for given. The neural networks can be used for both classification and numeric prediction. For classification, one output unit may be used to represent two classes. Represents one value 1 represents one class and the value 0 represents the other. If there are more than two classes, then one output unit per class is used. There are no clear rules as to the best number of hidden layer units. Network design is a trial and error process and may affect the accuracy of the resulting train network. The initial values of the weights may also affect the resulting accuracy. Once a network has been trained and its accuracy is not considered acceptable, it is common to repeat the training process with a different network topology or a different set of initial weights. Backpropagation learns by iteratively processing a dataset of training tuples, comparing the network's prediction for each tuple with the actual known target value. The target value may be known class label of the training tuple or a continuous value. For each training tuple, the weights are modified so as to minimize the mean squared error between the network's prediction and the actual target value. These modifications are made in the backwards direction through each hidden layer down to the first hidden layer. Although it is not guaranteed, in general the weights will eventually converge and the learning process stops. The back propagation algorithm is given. A neural network learning for classification or numeric prediction using the back propagation algorithm. Input to this algorithm a dataset D consisting of the training tuples and their associated target values. L is the learning rate. Network, a multi-layer feed-forward network. Output from this algorithm is a trained neural network. Initialize the weights. The weights in the network are initialized to small random numbers. Each unit has a bias associated with it. The biases are similarly initialized to small random numbers. Each training tuple X is processed by the following steps. Propagate the inputs forward. First, the training tuple is fed to the network's input layer. The inputs pass through the input units unchanged. That is, for an input unit J, its output Oj is equal to its input value Ij. Next, the net input and output of each unit in the hidden and output layers are computed. The net input to a unit in the hidden or output layer is computed as a linear combination of its input. Each unit has a number of inputs to it that are in fact the outputs of the units connected to it in the previous layer. Each connection has a weight. To compute the net input to the unit, each input connected to the unit is multiplied by its corresponding weight and this is summed. Given a unit j in a hidden or output layer, the net input ij to unit j is, where wij is the weight of the connection from unit I in the previous layer to unit j. Y is the output unit of Y from the previous layer and J is the bias of the unit. The bias acts as a threshold in that it serves to vary the activity of the unit. Back propagate the error. The error is propagated backward by updating the weights and biases to reflect the error of the network's prediction. For unit J in the output layer, the error J is computed by the formula has been given in the left hand side. The weights and bias are updated to reflect the propagated errors. Terminating conditions are training stops when change in the weight in the previous epoch are so small as to be below some specified threshold. The percentage of tuples misclassified in the previous epoch is below some threshold. A pre-specified number of epochs is expected. Sample calculation for learning by the backpropagation algorithm. The example shows the calculation for the backpropagation given the first training tuple x. Sample calculations are given in the screen. Calculation of the error at each node shown in the first table. Net layer and output calculations are given in the second table. Initial input, weight and bias values are shown in the third table. The calculation for weight and bias updations are shown on the screen. To classify an unknown tuple X, the tuple is input to the trained network and the net input and output of each unit are computed. There is no need for computation and backpropagation of the error. If there is one output node per class, then the output node with the highest value determines the predicted class label for X. If there is only one output node, then output value is greater than or equal to 0.5 may be considered as belonging to the positive class, while values less than 0.5 may be considered negative. Support vector machine. Support vector machine is a supervised machine learning algorithm which can be used for both classification or regression challenges. It is mostly used in classification problem. In this algorithm, we plot each data item as a point in n-dimensional space. And then we perform classification by finding the hyperplane that differentiate the two classes very well. Generally, support vector machines are considered to be a classification approach. It can easily handle multiple continuous and categorical variables. Support vector machine constructs a hyperplane in multi-dimensional space to separate the different classes. The core idea of support vector machine is to find a maximum marginal hyperplane that best divides the dataset into classes. Decision vectors are shown on the screen. Negative hyperplane and the red dotted line, blue color line showing the maximum margin, and positive hyperplane on the above the upper side of the green color line showing. All the support vectors shown on the green color. Support vectors are the data points which are the closest to the hyperplane. These points will define the separating line better by calculating the margins. These points are more relevant to the construction of the classifier. A hyperplane is a decision plane which separates between a set of objects having different class membership. A margin is a gap between the two lines on the closest class point. This is calculated as the perpendicular distance from the line to support vectors are closest to points. If the margin is larger in between the classes, then it is considered a good margin. A smaller margin is a bad margin. How the support vector machine works. The main objective is to segregate the given dataset in the best possible way. The distance between the either nearest points is known as the margin. The objective is to select a hyperplane with the maximum possible margin between support vectors in the given dataset. SVM reaches for the maximum marginal hyperplane in the following steps. Generate hyperplanes which segregates the classes in the best way. Select the right hyperplane with the maximum segregation from the either nearest data point. Some problems cannot be solved using linear hyperplane. In such a situation, SVM uses a kernel function to transform the input space to a higher dimensional space as shown on the right. The data points are plotted on the x-axis and z-axis. Now we can easily segregate these points using a linear separation. K nearest neighbor algorithm. An idea that can be used for machine learning as does another maxim involving poultry. birds of a teacher flock together. In other words, things that are likely to have a properties that are like. We can use this principle to classify the data by placing it in the category with the most similar or nearest neighbors. In a single sentence, nearest neighbor classifiers are defined by their characteristics of classifying unlabeled examples by assigning them the class of the most similar labeled examples. Despite the simplicity of this idea, nearest neighbor methods are extremely powerful. Computer vision applications, including optical character recognition and facial recognition in both still images and video, are used. Predicting whether a person enjoys a movie which he has been recommended, identifying patterns in genetic data to use in detecting specific protein or diseases. The KNN algorithm begins with a training dataset made up of examples that are classified into several categories as labeled by a nominal variable. Assume that we have a test dataset containing unlabeled examples that otherwise have the same features as the training data. For each record in the test dataset, KNN identifies k records in the training data that are the nearest in similarity, where k is an integer specified in advance. The unlabeled test instance is assigned the class of the majority of the k nearest neighbors. In the table shown on the screen, ingredients are given like apple, bacon, banana, carrot, and celery and cheese. Their attributes are given, their features. First feature is the sweetness, second feature is the crunchiness. Based on this one, these item ingredients are classified as a fruit, protein, or either or vegetable. Based on the features of the item that has been shown on the plotted on the graph. How sweetness in the sense, cheese is very less sweet and less crunchy. Lettuce is high crunchiness and less sweet. But if we take a look at the apple, high sweetness as well as the high crunchiness it's available. Based on this, the feature value, it has been plotted on the graph. So based on these items, some of the items have been grouped together as vegetables, proteins and fruit category. Now the given problem is to classify the tomato belongs to which category. Now we can find the distance between neighbors as well as the tomato. Locating the tomato's nearest neighbors requires a distance function or a formula that measures the similarity between two instances. There are many different ways to calculate the distance. Traditionally, the KNN algorithm uses Euclidean distance, which is the distance one would measure if you could use a ruler to connect two data points. So it is given in the previous figure by the dotted lines connecting the tomato to its. As shown on the screen, Euclidean distance is calculated between the P1 and P2. The Euclidean distance is specified by the given formula where P and Q are the examples to be compared. Next one, the distance formula involves comparing the values of each feature. The sweetness and crunchiness. The green bean and the green bean equals to sweetness equal to 3 and crunchiness equals to 7. We can use the formula. Based on the features of the ingredient, the distance to the tomato is calculated. Distance to the tomato grape is 2.2, green bean is 4.2, nuts is 3.6, and orange is 1.6. Deciding how many neighbors to use for KNN determine how will the mood will generalize to the future data. The balance between overfitting and underfitting the training data is a problem known as the bias variance trade-off. Choosing a large K reduces the impact or variance caused by noise data, but can bias the learner such that it runs the risk of ignoring small but important patterns. Appropriate K value. K value initially set to 0. At that time, the error rate is very high. When the K value is increasing, automatically the error rate is decreasing. At one particular, that bending point can be noted, it is at 10. Then again, the error rate is increasing. So where the minimum error is shown on the screen, that value, that K value can be chosen for the problem. In practice, choosing a k value depends on the difficulty of the concept to be learned and the number of records. K is a set somewhere between 3 and 10. One common practice is to set k equal to the square root of the number of training tuples. The traditional min-max normalization method can be used for rescaling the features for KNN. Lazy learner is not really learning anything. It merely stores the training data in it. It thus allows the training phase to occur very rapidly, with a potential downside being that the process of making prediction tends to be relatively slow. Due to the heavy reliance on the training instances, lazy learning is also known as instance-based learning or rote learning. Lazy learning algorithms are k-nearest neighbors, local regression, or lazy neighbor and weaknesses of K-NN algorithm. A strength side simple and effective, makes no assumption and fast training phase. Weakness side does not produce a model. Slow classification phase requires a large amount of memory. Nominal features and missing data require additional